Alright, so hello and welcome to this video tutorial for RC Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 6 here, which is a method of joints problem. It's asking us to determine the forcing members BC, CF and FE, state if the members are in tension or compression. So I've kind of replicated the diagram on the right here just so that we can make an absolute mess of it. Before getting into any of these problems, I feel a good place to start is often to recognize these supports. So at points A and G, we've got fixed supports here, and so we can add some external forces to our diagram. Let's go ahead and do that. So we've added our external forces here. One thing to note, however, is at joint G, if FGY existed, there would be nothing vertical to counter it, right? So we can almost rule out FGY as a force here, and we're left with these three external support forces. Okay, so let's get started with this problem then. So almost immediately by inspection, we can say that FA, Y here is equal to £2,000. The reason we can say that is because the truss as a whole is in equilibrium. We've got £2,000 of force acting down, and so we must have £2,000 acting up, and the only force acting up here is FA, Y. We can note as well that FA, X and FG, X are going to be countering each other in the horizontal direction. Maybe we should redraw. We can redraw one of these arrows later to show one pointing to the left and one pointing to the right. But basically, we can say FG, X and FA, X are equal to each other. From here, I'd probably take moments. So we can solve for either FA, X or FG, X by taking moments about A or G. Let's take moments about G, so we can say the sum of moments acting at G acting clockwise is equal to 0, since this system is in equilibrium. Therefore, things acting clockwise are equal to things acting anti-clockwise. So what moments do we have acting clockwise? Well, we've got this one at B, C, and D here. So at B, we'll have 4 times 600. At C, we will have 8 times 600. And at D, we will have 12 times 800. And we can say this is equal to things acting anti-clockwise. What do we have acting anti-clockwise? Well, we've got this FA, X, which is 4 feet away from point G. So we can say for FA, X. When we put this left-hand side into our calculator here, we get a value of 16,800. And we can say this is equal to, for FAX still, and we can then divide by 4 on both sides. So we can say, therefore, FA, X is equal to 4,200. We could then add that to our diagram here. I could rub out FA, X and replace it with 4,200. Since we established earlier that FG, X and FA, X are equal to each other, FG, X takes a value of 4,200 as well. However, we note that it'll act to the left to counter FA, X acting to the right. So let's just rub that out over here. And let's change this arrow over here so that it's acting to the left at point G. Okay. And it takes a value of 4,200. And we calculated earlier that FA, Y is equal to £2,000, so we can add that to our diagram as well. Okay, so we're in a good place with the problem now. Since we have all our external forces, let's go ahead then and move to our internal forces. I would look here at point G, because we know we've got that 4,200 acting to the left. Well, to counter that then, we must have 4,200 acting to the right there. So let's add that in. And then since the member FG is in equilibrium, we must have 4,200 acting to the left at point F here as well. So we've already started adding some forces there, some internal forces. I'd also look at point B. We note that we've got a 600-pound force acting down. The only thing that could counter that would be BF. So we must have a 600-pound force acting there as well. And then since member BF is in equilibrium, we can add a 600-pound force acting down at point F as well. From here, I'd look for joints where we have two unknowns. So right now I'm looking at joints A and joints D. A, we don't know the force in member AB, and in AF and joint D, we don't know the forces acting in CD and DE, right? Let's start with joint A then. So let's just make some room here. Joint A. So let's just draw a little free body diagram here representing what's going on at joint A. Note that we know that there's a 45-degree angle here since you've got a square right here. You've got a 4x4 square. Okay, so we have a free body diagram here for joint A. Let's go ahead. Does it really matter what order we do it in? I don't think so. Let's resolve. You know what? Let's resolve vertically first, since AB here doesn't have a vertical component. So we can say the sum of forces in the y are equal to 0. Therefore, what's acting up is equal to what's acting down. What's acting up? Well, we have that 2,000-pound force there. What's acting down? Well, we've got the vertical component of AF there, which we could describe as AF sine 45. Naturally, then, we could divide both sides by sine 45, so we can say 2,000 over sine 45 is equal to AF. Therefore, AF, when we bung that into our calculator, gives us a value of 2828.4 pounds. Okay, so we've got one of our solutions there. Let's go ahead then and resolve horizontally. So we can say forces in X are equal to 0, therefore things acting to the left are equal to things acting to the right. Let's look at things acting to the left. So we've got AB, and then we've got the horizontal component of AF. Note, AF is acting at a 45-degree angle here. What that means is its horizontal component is equal to its vertical component. And we established earlier that 2,000 is equal to its vertical component. So we could just go ahead then and write in 2,000 here for the horizontal component of AF. What's acting to the right? Well, we've got that 4,200. Okay, so we can rearrange this. We can say, therefore, AB is equal to 2,200. Subtracting 2,000 from both sides there. Let's go ahead and add these forces to our diagram here. Now again, we can add some more internal forces since members AF and AB are also in equilibrium. Okay, apologies that my diagram is getting a little bit messy here. So we've added this internal force here, this 2,200 pound force acting on joint B. Note then that there must be an internal force acting here, which is also 2,200 pounds to counteract that. the problem's kind of unraveling here, right? So if that's acting there, member BC is in equilibrium, so we must have a force acting to the right here that's also 2,200 pounds. Okay, so I mentioned earlier that joint D is also a good place to look at since it has two unknown internal forces, right? Let's go ahead then and resolve at joint D. Let's just make some more room here. So joint D. Let's go ahead and draw a free body diagram at joint D. Okay, let's start by resolving vertically to solve for a DE here. So we can say the sum of forces in the y are equal to 0. Therefore, things acting up are equal to things acting down. What's acting down? Well, we've got that 800-pound force there. And what's acting up? Well, we've got the vertical component of DE. So we can say, we can describe that as DE sine 45. Let's divide both sides by sine 45 here. So we can say 800 over sine 45 is equal to DE. And when we put that in our calculator, that gets us a value of 1,131.4 pounds. Okay, let's go ahead and resolve horizontally to solve for CD here. So things acting to the left are equal to things acting to the right. What do we have acting to the left? Well, we can use the same trick that we employed earlier. We kind of identified that the vertical component of DE is 800. For a 45-degree vector, the horizontal and vertical components are equal to each other, so we can say then, acting to the left, we've got 800, that's the horizontal component of DE. Acting to the right, we've got CD. Okay, well, don't need to do any transposing there. CD is equal to 800 pounds. Wonderful. Let's go back to our original diagram here and add those forces in. Again, since we've added forces at joint D here, we can go ahead and add more forces at joints C and E. So at E, we'll have that 1,131.4 acting as well. And at joint C, we'll have that 800-pound force acting to the left. We're almost there with this problem. To try and make things a little bit quicker or easier for ourselves, we note the fact that this 1,131.4 pound force is acting at a 45-degree angle, and we identified earlier that both its horizontal and its vertical components are equal to 800, right? So we could look at this 1,131.4 pound force acting at joint E, noting the fact that it's got a 800 pound vertical component acting down and 800-pound vertical component acting to the right. So kind of by inspection, without having to carry out any calculations necessarily, we can say that we've got 800 pounds acting to the left here and 800 pounds acting up here to counter that 1,131.4 pound force. So let's just add that to our diagram here. And again, we can kind of fill in the rest. So we'll have 800 pounds acting down on joint C here, and we'll have 800 pounds acting to the right at joint F here. It then doesn't really matter which joint we pick between joint C and joint F. Let's pick joint C, since at joint F we've got a diagonal force acting there. We'd prefer just to work with as few diagonal forces as we can, really. So we're picking joint C here. Let's go down. Let's create some more space. So joint C. Again, let's draw a free body diagram of joint C here. To keep things simple, I'm just gonna add that 800-pound force and that 600-pound force acting down and just turn it into a 1,400-pound force acting down. And again, for that 2,200-pound force acting to the right and that 800-pound force acting to the left, I'm just gonna convert that effectively into a 1,400-pound force acting to the right, right? Okay, so conveniently now we can, by inspection, tell that we're in a kind of correct place here, since we've got a vector acting at a 45-degree angle, and we note that its horizontal and vertical components are equal to each other. We could resolve vertically or horizontally. I would look at a situation like this and employ a different approach. I would actually use Pythagoras' theorem here, since we note that the horizontal component of CF is 1,400 and its vertical component is also 1,400. We could go ahead and, if you're unfamiliar with this, I'd suggest brushing up on your Pythagoras theorem, but I'd say, therefore, CF is equal to the square root of 1,400, or let's say 2 times, since they're equal to each other, 2 times 1,400 squared. Okay, and when we put that into our calculator, we get a value of 1,979.9 pounds. Okay. Let's go ahead then and add that to our messy diagram here. So we've got 1979.9 pounds here and 1,979.9 pounds acting here. Are we done? No. Evidently, the question is also asking us if the members are in tension or compression. What we could do is we could list out our members in the top of our workings here. We could say we've got AB, BC, CD, DE, EF. Oh my goodness, FG. And we've also got CF and AF and BF. Let's just check that. Okay, looks like I missed out CE there. Okay, and we could describe each of these members, whether or not they are in tension or compression. Let's go ahead and do that then. So AB looks like it's in compression. Let's just write out C for compression. BC is also in compression. CD is also in compression. DE is in tension. EF is in tension. FG is in tension. CF is in tension. AF is in compression. BF is in tension. And CE is in compression. Okay, so that's the problem. I quite like that problem, even though it's quite long. If you have any questions or comments, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.